Hello, hello, I am back again. And with this video, we're going to look at how Ohm's law applies to parallel circuits. Let me show you just a couple things, and then I'll work out an example for you. Maybe. All right, so in the last video tutorial, we looked at series circuits. That was when you have only one pathway for the current to flow. All the current is the same throughout the circuit, it has nowhere else to go. For total or equivalent resistance, you simply add up the total resistors, and that equals your total. And then the voltage drop across each component should add up to the total voltage provided by the battery source. Well, now you can see in a parallel circuit down here, you have more than one pathway for the electricity to take. So as electricity flows, let me go back to that picture. As electricity flows, it gets to this point right here, and say that's kind of like a fork in the road. Some of the electricity is going to go down this first loop, and some of it's going to keep going. Then we'll reach this branch here. Some will branch down into this loop, and then some will keep going. Now, it doesn't divide evenly. So you can't just assume there's an even distribution of current through each loop. All of that depends on the resistor that's in each pathway. So we're going to look now at how to apply Ohm's law to parallel circuits. So here are a couple of things to know. Again, we've already said the electric current is divided across multiple pathways, not necessarily evenly at all. Let's start at the bottom again for total current. This time, the current does have multiple pathways to go. And as we said, some of it's going to go down one loop, some of it's going to continue on another loop. So if we were to take all of the current in loop 1 and in loop 2 and in loop 3, it's all going to converge back together as it returns back to the battery. So for the total current leaving this battery, it's going to equal the sum total of the current in each branch. So I'll show you how to do that in just a few minutes. Unlike a series circuit, total voltage is the same in each parallel branch. So if there's a 9-volt battery source here, there's a voltage or a potential difference provided of 9 volts. That same 9 volts of potential difference or voltage will be present in this loop, and this loop, and this loop. So the voltage drop is equal in every branch of a parallel circuit. And then the equivalent resistance, or total resistance is another way of saying it. The equation is 1 over the equivalent or total resistance is equal to the sum of all of the inverses or reciprocals for the resistors, okay? So I'm going to talk you through how to do all of that, what all of that means, and how to apply this to this parallel circuit. I'm going to stop sharing this screen now and share my whiteboard with you. Okay, so here is the setup. This is the parallel circuit sketched roughly over here. We've got 3 loops in this parallel circuit. What we're going to call R1 is going to be the 90 ohm resistor. R2 is the 45 ohm resistor, and R3 is 180 ohm resistor. Okay, so that's filling in the resistances for each of those individual components. The other thing I know is that because this is a parallel circuit, the total voltage, which is 9 volts, again, it's a basic 9-volt battery, the total voltage is going to be the same in each branch or through each component in that parallel circuit. So I know that much now. At this point, I can calculate the individual current flowing through each of those resistors simply using Ohm's law again. So let's just go back to Ohm's law, V equals IR. And we want to calculate I. I is going to actually equal V over R. So for each individual resistor, I'm going to take the 9 volts, and I'm going to divide by the resistance, in this case, 90. So this is for the current flowing through pathway 1 or through resistor 1. And so that current is going to obviously equal 0.1 amps. We'll go over here. The current through loop 1 or resistor 1 is 0.1. We need to simply do the same thing. The voltage doesn't change, but now we're in loop 2 where the resistor is 45 ohms, and 9 divided by 45 is going to give us 0.2 amps of current through that loop or pathway. It's a 0.2. And then we'll do it once more for the 180 resistor. I want you to think about what you just saw in the first two loops. Will I have more or less current going through this resistor? What do you think? If you said less, you are correct. It's actually much less, 0.05. Let me get that decimal in there somehow. So what you see here is the greater the resistance, the less current. You may have heard the statement that electricity will take the path of least resistance. Well, if you look at your three loops here, loop 2, or the middle one, is the pathway that has the least resistance. 45 ohms is the lowest amount. And you see that's where the greatest amount of current flows, that 0.02 amps of current. So let's finish filling our chart here. We're going to end up with a total current of 0.35, if I did my math correctly, 0.1 plus 0.2 plus 0.05. What happens is that current, I'm going to label it I up here in our diagram, it leaves the battery and travels that way. And like I said, some goes down this branch and some keeps going. Then some goes down this branch and some keeps going around here. But it all converges back together. And so by the time we get back here, that same 0.35 amps of current that left the battery has now all come back together again. And I've got 0.35 amps of current returning. Now, let's talk about the resistance. At this point, because of the information I have in my table, I can look at the total voltage and the total current and come up with my total overall resistance very simply here. My total current is, get my pen back. My total current is 9 volts. Sorry, my total voltage is 9 volts. My total current is 0.35. And so the total resistance is 25.7. Solving for that R total for the whole circuit, R equivalent is what we call it, R total is going to be 25.7 ohms. Now, I do want to show you though, if I did not have total voltage or total current, I could still have determined my total equivalent resistance by understanding how to determine equivalent resistance in a parallel circuit. The equation for equivalent resistance, 1 over the equivalent or total resistance equals 1 over basically the sum of all of the reciprocals for the resistors, individual resistors. Okay, so 1 over the total equals 1 over 90 plus 1 over 45 plus 1 over 180. Now be careful, this is kind of like our mirror equations we were doing before spring break and stuff. We're adding up reciprocals and that equals 1 over what I'm trying to find. So 1 over this, even if you just add up all of these fractions, I'm going to convert it to a decimal. It's 0.038 repeating basically. That is not your answer. That's 1 over the equivalent resistance. So you need to take the inverse of this. Just take the inverse of that and you will see, you'll verify it's exactly what you expect it to be. It is in fact 25.7. So this is the rule for resistors in parallel. It's the inverse of the sum of the reciprocals. Okay? We can calculate power again. Power is still going to be P equals I times V. So we'll go ahead and do that just real quickly for each one. I times V, 0.1 times 9 for resistor 1 would be 0.9. For resistor 2, 0.2 times 9 is going to be double that, so 1.8. And 0.45, I believe, for the third one, it's half of the first. 0.05 times 9. 0.45. And again, the total power is not really applicable. So you can see here, the greater power is going to result in the brightest light bulb. And that's how you apply Ohm's law to parallel circuits. Make sure you do your practice problems, ask questions about the lab if you need to, and be ready for your quiz. See you soon.